So this course, particularly industrial homogeneous catalysis, we are also discussing principles and mechanism. Today, we will mainly focus on alpha and beta migratory insertion. We'll also touch upon little bit on the topics that we were discussing in the last class. As you would remember, in the last class, we were discussing oxidative addition. In essence, we are trying to look at ligand metal complexes, which are reactive metal complexes. It can insert into a small molecule. Such over here, the below, as you see, the bromobenzene. It could be many other different molecules. Let's say we are calling it as X and Y. We want to insert this ligand metal complex into the bond of X and Y. So to speak, in the picture below, we are interested in inserting the metal in carbon bromine bond in the bromobenzene that is out here, right? What we have noticed in the last class that the oxidation state of the metal will be raised by 2 units. As we have said, if it is palladium 0 oxidation state, then after oxidative addition, it will be palladium +2. If it is nickel 1+ complex, we start with, after oxidative addition, it would be nickel +3. Here is a real example of a palladium complex. The way this complex is synthesized simply is, of course, you take 4 equivalent of triphenyl phosphine and some palladium 0 precursor. This is one of the way to synthesize it, or you can of course reduce the palladium 2 and come to palladium 0, and then you essentially prepare palladium tetrakis or tetra-triphenyl phosphine complex. From there, 2 of the phosphine ligand goes out. What you get is a very reactive intermediate, that is palladium, which is now ready to be incorporated inside this carbon bromine bond. Palladium was palladium 0 oxidation state. Here you get palladium 2+ oxidation state. So 2 phosphine ligand there, bromide, this is coming from here, the starting material, and the carbon center, which is over here. So this becomes minus, this becomes minus, palladium 2+. Okay, there are many such type of reaction. Both the metal complexes can change, as well as this XY, which is over here bromobenzene, it can change. But one good thing that has happened in the process, it has allowed a metal carbon bond formation. This is a very reactive intermediate, as you will see many times that this sort of intermediate will go on to give many exciting chemistry which are relevant industrially. I will come back in few minutes, some of those industrial processes. Now, opposite of this oxidative addition inside XY we were inserting the metal. Reductive elimination is opposite of that. That means the metal is already inserted into XY. You get ligand metal complex and regenerate XY. Now, as you know, a reaction can go back forward as well as backward, right? These things are happening almost in equilibrium, but the requirement for oxidative addition is just opposite for that reductive elimination. Let's go back once again. Usually, if you have a ligand like here phosphine ligand, right? If you have a ligand which is holding to the metal center, if this ligand is small and electron rich, then you will get the oxidative addition into XY. When metal has a lot of electron, or the electron density is very high, then it will feel like inserting into the XY bond, right? So ligand has to be small and electron rich. That's when this process of oxidative addition happens very faster. On the other hand, let's say you want to do the reductive elimination. That means opposite of this oxidative addition. That means you have started from here and you want to go back in there, right? For that purpose, let's go again to the reductive elimination. For that purpose, if you want to move the reverse reaction, that means from this metal complex, oxidative addition metal complex, if you want to regenerate the ligand metal complex as well as XY, what you need to have is a ligand which is bulky, big, as well as electron deficient. So then only you are going to have the reductive elimination. So just relax and think about it. Oxidative addition is in the forward sense, for example. Reductive elimination is in the backward sense. Now for doing this reaction in a forward sense, you have to have small ligand as well as electron rich ligand, because it is going to insert into the XY bond. But for, let's say, some application, you want to do the reverse, where oxidative addition is already there, you want to get back to the starting material or the constituents. Then what you have to take is the ligand which is big, because then these XY will feel like they don't want to stay with metal, and metal is in high oxidation state. As I said, ligand, electron rich ligand will stabilize it, but if you have electron deficient ligand, they cannot stabilize the higher oxidation state metal. Then what will happen in the process? XY will fall apart and come out, and you will regenerate the ligand metal. Is it getting little bit clear? The requirement for oxidative addition is just opposite to that of the reductive elimination, because it is forward and backward reaction, right? For oxidative addition, you will have electron rich ligand. For reductive elimination, you will have electron deficient ligand. For oxidative addition, you want a small ligand, less sterically bulky ligand. For the reductive elimination, you need a bulky or big ligand, fat ligand, big ligand. Okay, so this is just an example of reductive elimination, where you see that between benzene carbon as well as this acetyl carbon, this alkyne center, the carbon-carbon bond formation is going on. Okay, now both this oxidative addition as well as reductive elimination you will be seeing again and again in the industrial scale reactions. That's why it is important to fundamentally discuss these things, and the requirement, as I said, is pretty important to remember. Today, as we said, the topic is alpha migratory insertion. What is happening here? This is a little bit different reaction, but quite exciting reaction. What is happening here? You have two units on the metal center. Let's say this is the metal center, this is a methyl group, and this is a CO. What essentially happened that this R group will be transferring on the carbon of this carbonyl. Okay, it need not be necessarily carbonyl, it could be olefin, it could be anything else, usually an unsaturated molecule. In this right hand picture, it is a little bit more clear. So metal carbonyl, this R group which is with metal, it will transfer on this carbon. Okay, so with respect to metal, this is alpha carbon, this is beta atom, alpha beta, and with respect to metal, this is alpha. So at the alpha position of this unsaturated molecule, this attachment, whatever is there, it could be any alkyl group, hydride, you name it, any substituent it could be, if it is transferring at this alpha position, not at the beta position. This is alpha position, this is beta position. If a substituent which is attached with metal is transferring to another substituent which is also attached with metal, this is what is called alpha migratory insertion. Okay, now if you look at this cartoon, one of the substituent on the metal, so one of the hand of the metal is transferring basically on the other hand of the metal. Okay, of course metal can still have other ligand which I have not drawn over here. Okay, so it's not necessarily has to be carbonyl, it could be any other molecule, but this general phenomena has to follow. As you can see, this transferring group could be hydride, alkyl, alkoxide, amide, or Nr2 minus. Many different substituent can transfer. Okay, we'll come to a moment in terms of industrial application. In the next slide, we'll come to that. Okay. Now, in the beta migratory insertion, what we see essentially is, of course, this transferring group is not attaching at the alpha position. See here, transferring group was attaching at the alpha position, right? At the alpha position, this transferring group is attaching. Here, the R group is attaching at the beta position. With respect to metal, this is alpha position, this is beta position. At the beta position, this R group is transferring. So there was an olefin interacting with metal. In the process, what happens? R group transfer over here, and metal alkyl, the whole alkyl group, is now transferred on it. Right? So this is what is called beta migratory insertion. Now, usually the energy demand for beta migratory insertion is little less compared to the alpha migratory insertion. But then there are places where only alpha migratory insertion would be happening. Okay, we'll come back and discuss those. Now, for example, over here, as you see a real example where you have a metal and a methyl group. Now, methyl group transfer on this CH2, this is CH2, and this is the second CH2. So at the alpha beta position, methyl group is transferring. As I said, this sort of transferring group can be varied. It could be a hydride, that means H. It could be an alkyl, that means R, general formula. It could be alkoxide like OR, or it could be amide as it is shown in here. Now, so far then, you have seen 4 different fundamental type of reaction. Fundamental type of reactions are very few. So immediately once we are done, maybe a few more classes, 1 or 2 more classes will be done, and then we'll be able to see the application of these methods into the industrial scale. I'll come back very quickly to those aspects. Just to summarize so far what we have discussed, we have taken a ligand metal complex and inserted into a small molecule. In the process, that was of course the oxidative addition, ligand metal complex we inserted into XY. Okay, we have taken a ligand metal complex where 2 substituent of the metal is leaving it and forming bond between them, that is reductive elimination. We have discussed right now the alpha migratory insertion. So the migrating group, that is Z over here, or Z, this migrating group is transferring from the metal center to the adjacent, right adjacent ligand which is attached with the metal center. For example, over here, methyl group is transferring onto the CO, okay, to give you an acyl unit, CH3COM. Okay, so for example, if you are looking at it, if you protonate this, you can get acetaldehyde, right? So carbon monoxide and methyl group which is attached with it and a proton or a reductive elimination from hydride can give you acetaldehyde, which is fantastic, right? Okay, so I'll come in a moment. This R group is transferring on CO to give you COR. As I said, it need not be CO, anything else is also possible. Another type of reaction, fourth type of reaction that we have discussed here briefly, is this transfer of R onto this olefin. So what we get is metal alkyl species. So metal CH2 and this R. R is the transferring or migrating group, okay, onto the unsaturated olefin. Now this transferring group can be varied as you have seen in here. Moving on, let's look at some of the real life example or the industrial scale example for these processes. This process is called the first one. There are many reactions where you will see, of course, both alpha migratory insertion, beta migratory insertion, oxidative addition, reductive elimination, all these reactions are happening. Here is an example. Okay, this is propene. Okay, 1, 2, 3, 3 carbon with an olefinic double bond. This is a propene, right? Now from this propene, as you see here, you are reacting with CO plus hydrogen, right? So CO plus hydrogen, carbon monoxide gas and hydrogen gas. It's a high pressure reactor. If you put these two gases together along with this olefin, which is also a gas, all these three gaseous material put together, if you add a suitable rhodium catalysis or cobalt catalysis, or then you can get this, or even iridium catalysis, you can get these two aldehyde. This is called branched aldehyde. This is called linear aldehyde. Now, can you draw the mechanism, whatever is happening here? What we have discussed so far in the class is good enough to understand the reaction mechanism. Let me go slowly on that. So you start with a rhodium complex where oxidative addition into this hydrogen gas is going on. We'll come back to hydroformylation later as well. But what is essentially happening, this rhodium salt that you started with, oxidative addition has gone into it. So it has your rhodium hydride, carbon monoxide under high pressure, these are under all high pressure, carbon monoxide attached with it, olefin also attached with it. See, with this metal center, essentially three gases are attached. This hydrogen gas undergone oxidative addition. Remember in the last 3 slides we were discussing this, where a small molecule is really activated and metal is inserted into the XY bond, right? Let me get back to you. So this XY, if it was H and suitable rhodium precursor, it will incorporate into this XY bond. So then you have X rhodium Y. So X rhodium Y, for example, that has happened in here, X rhodium Y. Okay, so X Y is this hydrogen gas. Rhodium has incorporated oxidatively into the hydrogen gas, and CO bound with rhodium, olefin bound with rhodium, right? Now what could happen, as you have seen, at this point you can have the alpha migratory insertion, okay, as well as a beta hydride transfer. So right? Overall, you see this is an alpha migratory insertion is going on, where you see on the on this olefin and carbonyl, this at the alpha position of carbonyl, this olefin is getting attached, right? Okay, so this is where overall you see this exciting transformation is going on, and this hydride will then transfer into the um, into this alpha position of carbonyl to give you the aldehyde, right? So this is the intermediate for the terminal aldehyde. Okay, so by using this hydroformylation reaction in industry, metric tons of these materials are being synthesized every day in many industries. These hydroformylation reactions, of course, has to overcome many limitations such as high catalyst loading, high temperature, pressure. It has to be minimized of all these different gases, many different side product. In this case, the two competitive products are this branch product, where aldehyde is bound in the middle, as well as terminal product, which aldehyde is bound in the terminal position. As you see, aldehyde is at terminal position. In this case, aldehyde is at branched position, right? So all these product formation, all these two product formations are competing depending on usually the reaction condition, often the ligand on these metal centers. We can control one product formation predominantly over the other one. So there exists an opportunity to create one product versus another one. Another exciting transformation here could be that since this is happening in the middle, so this center, this carbon center can be stereogenic. So an asymmetric synthesis when these two substituents are different is also an exciting opportunity here. Okay. Now I hope this alpha migratory insertion, which would be happening, let's say over here, hydride will transfer at the alpha position, and the reductive elimination, you can say that as a reductive elimination as well, that is going to happening in this position to give you the corresponding aldehyde. Okay. Do you have any of you have any question at this point? Okay, if there is no question, we can move on. So this is an exciting transformation once again. By taking three different gases, three different units put together, an olefin, carbon monoxide and hydrogen, you get an exciting product which is having much higher value than these. These are the fine chemicals, depends. These are the fine chemicals industry needs. These are the things that is required for many other pharmaceuticals and agrochemical preparation. These you can see as a building blocks. Of course, CO, hydrogen and olefin was building block, but from these simple building blocks, a little more complex building blocks were prepared, like this aldehyde, CH3, CH2, CH2, CHO. This is a butyraldehyde. This butyraldehyde would be excellent transformation from these three simple gases. So we have encountered alpha migratory insertion and reductive elimination in the process to convert it into these important molecules. Okay.
Excuse me, sir. Can I ask one question?
Yes, Mamta.
In this aldehyde, so these separated, how we separate this by the boiling point, or any some method we used for this
For
on this
the
step?
for this aldehyde,
I,
you mean?
yes, yes,
Two
as a
aldehydes.
project.
Okay, so these two aldehydes, if they are forming of course, this is something you don't want them to be forming because the properties will be similar. These two aldehyde, like branched aldehyde and linear aldehyde. So
Yes.
you would first of all like to have a method which can give only one product. Okay, this is where you make the reaction perfect. You tune the ligand for the metal center. Okay, you tune the reaction condition, you tune everything so that predominantly or exclusively you get only one product, any one of these products. Now if one of them is forming in, I mean, these, I would say often you have to run column. It depends on the type of aldehyde, of course, but these will be very difficult mixture to separate out otherwise. Okay,
Yeah, yeah.
in
Understood.
industrial scale, because these, the properties of both of these aldehyde would be similar, right?
Similar, yeah.
Very similar. So
Yeah.
this is why you want to develop a catalyst which will be very useful in preparing only one molecule. If whatever
Okay.
impurity is there, whatever other product is there, depends. Sometimes what happens is in the next step it may get filtered, right? In the next step you might will do something which will predominantly react with only one of them. That could be one way to separate them, but otherwise you have to do some synthetic technique to separate them out, right? Just like in a synthetic laboratory, depends
Yeah.
what is your purpose. Yeah, these are very problematic issues to deal with because these both of them are nearly similar. Of course, if you run a column, definitely you will have an opportunity, and there would be a way, depending on what aldehyde you have, there would be a way to separate them out. Okay. Okay, then. So, but I
Thank you.
think yeah, the most important point is it's a very, very simple three gases: carbon monoxide, hydrogen, and olefin. This propene is also a gas. From there, you get a high value compound, and these are truly happening in metric tons of industrial scale. These are, people have by now, because there is a lot of history behind it. If you want, you can read a lot about the hydroformylation reaction, what metal it started with, now which metal we are using, and which are the industry using it, what are the problems facing. We'll come back to these in a different context, but these are happening, I mean, these are happening mainly because these are the materials for many other pharmaceutical synthesis, drug synthesis, material synthesis. These are fundamental type of reaction. These are, of course, has to be very cheap reaction. The catalyst loading is very, very effective. Things are happening very, very perfectly for this. We'll come back to this transformation later. But I was just wanted to discuss in the context of simple transformations or simple reaction type that we have discussed so far, and wanted to show how this simple principle can be applied to prepare these useful industrial processes or compounds. Okay, now let's go for another important reaction, which is Monsanto acetic acid process. Again, this is a very, very famous reaction. Quite important reactions. Acetic acid, the vinegar we use for, let's say, cooking purpose or many other purpose, right? Vinegar we use everywhere. So acetic acid, vinegar is nothing but acetic acid. So how acetic acid is getting prepared worldwide, in the world supply of acetic acid is done by this reaction, okay, which is known as Monsanto acetic acid process. What you are having here, methanol. Of course, this is not the alcohol we drink, whoever drinks. It's the ethanol. Methanol is poisonous for our body. If anybody is consuming methanol, that is deadly. So a lot of time we hear in our country, let's say, some of the people are drinking alcohol, and some very unfortunate incident happen. We see the reports in the newspaper that people died out of alcohol drinking. These are one of the reason of this alcohol related death is that there was this methanol involved in it. Of course, there could be other reason, I'm not getting into that, but methanol could be very poisonous for our body because our body cannot process methanol. Ethanol can be processed, ethanol to acetaldehyde, and then from there, acetic acid, carbon dioxide, and other fragmented part can go out by Krebs cycle, for example. But methanol, oxidation of methanol is not easy for our body. It requires much more energy compared to ethanol. So any impurity or any consumption of methanol could be potentially deadly. Okay, so anyway, these methanol, as you know, these are very commodity material. A lot of quantity of these methanols are there, and this can be generated from carbon dioxide, for example, or many other sources that we may or may not discuss in this course. But methanol, which is present from industry or coming from industry in large quantity, simple chemical, putting along with carbon monoxide, we are getting this this acetic acid. Essentially, what you can see, just roughly, that carbon monoxide is inserted between the methyl and oxygen bond. Methyl and oxygen bond, carbon monoxide is inserted. Of course, that's not the mechanism, right? CO cannot insert, or it's not an oxidative addition of CO into methanol. CO is as if CO is just inserted into methanol. Okay. Now I will discuss how this is happening briefly. These are the processes, we'll come back in future, but let me briefly discuss it here, the way this reaction is happening in the context of alpha migratory insertion. What we do in this case is you take methanol, carbon monoxide, rhodium or an iridium catalyst in presence of catalytic amount of hydroiodic acid, HI. Without this, reaction really doesn't work well. And then you get this acetic acid. What is happening here? First, this methanol reacts with HI, hydroiodic acid, okay, just like HCl, okay, or HBr, hydrobromic acid. So HI, hydroiodic acid, reacting with methanol to give you methyl iodide and water. Methanol and hydroiodic acid give you water and methyl iodide. Now this methyl and iodide has undergone oxidative addition. Going back again, referring back to the first discussion, X and Y, methyl and iodide, and you are taking rhodium or iridium, inserting it into here, like here. So this is methyl and this is iodide. Methyl, iodide, and rhodium or iridium metal complex inserted into methyl iodide. So you get rhodium methyl iodide complex. Okay, I'm not getting into the reaction mechanism as we were discussing in the last class. Oxidative addition mechanism can vary. It could be SN2 type of mechanism, it could be radical type of mechanism, it could be concerted type of mechanism, right? Those we have discussed briefly. But overall, even if you want to forget about the reaction mechanism, it could be that if rhodium was rhodium 1 plus to start with, after oxidative addition it becomes rhodium 3 plus, right? Rhodium 3 plus if it was rhodium 1 plus to start with. Now with methyl and iodide, that means from methanol and HI, you get methyl iodide, you get oxidative addition. That's the first application of oxidative addition, let's say. Okay, very simple. You have seen in the last slide oxidative addition into hydrogen gas. Just metal insert into the hydrogen bond, right? Metal inserts into hydrogen bond. That is the oxidative addition into hydrogen gas. Here rhodium, the metal, inserts into methyl and iodide bond to give you a rhodium high valence species, like let's say rhodium 3 plus with methyl and iodine there. CO, carbon monoxide. You know carbon monoxide can attach with metal center. There is a sigma bonding as well as a pi back bonding. As you know, carbon monoxide through carbon, it donates rhodium, and then there is a back donation could be possible depending on the metal and amount of electron involved. There would be a back donation. So sigma donation and pi back donation are possible. So rhodium CO complex will be generated very easily. Now on this carbon monoxide, this methyl unit is transferring on the carbon, not on the oxygen. If it was on the oxygen, it would have been beta migratory insertion. This is going to be on the carbon. As you see on the carbon, methyl group is migrating, alpha migrating insertion. Okay, and then this iodide and this acyl unit undergo reductive elimination. The X and Y, or X and Y stitching together, joining hands to give you CH3COI. Simple. So you see how many principles we have applied here. Almost everything that we have learned so far: oxidative addition, alpha migratory insertion, and reductive elimination, right? So all these three principles, what we have learned here, have been applied into the Monsanto acetic acid process. I think that's quite exciting, right? What we have learned here again from the last class: oxidative addition, reductive elimination, alpha or beta migratory insertion. You see, three processes out of the four things we have discussed here is industrially very much important. And the vinegar that we use in our kitchen every day, or whenever it is required, it is being prepared by this method. What we do here, we have taken methanol, that is here methanol, carbon monoxide, which is a gas. Of course, it's a deadly gas. If anyone consume, it's usually very poisonous gas. Oh, sorry. As you have seen here, methanol, carbon monoxide, methanol, carbon monoxide, and HI, hydroiodic acid. Once again, if you don't add HI, this reaction really doesn't work well. Why HI is required? Because oxidative addition into methanol is not feasible. You have to convert methanol into methyl iodide with the help of HI. What happens in the process? You prepare methyl iodide and water. Methanol plus HI give you water and methyl iodide. Once methyl iodide is generated, from there you get the oxidative addition into the by the rhodium complex onto the methyl iodide bond. So that's the first step. I did not show it here. Okay, methyl iodide oxidative addition. Of course, CO is bound with the rhodium, and then alpha migratory insertion onto the CO. So the carbon, oxygen on the carbon, methyl attached. If you see, carbon has again over here 4 hands, 1 hand, 2 hands, 3 hands, and 4 hands. Over here, this carbon also has 1, 2, 3, 4. Anyway, so overall, then this iodide, which is ready, this iodide and COMe undergo reductive elimination. Okay, of course, this is an electron deficient partner, right? COMe is an electron deficient species. As I was also telling, for reductive elimination, you need electron deficiency at the metal center, which is, of course, acyl is one of such substance or substituent where you can have ready reductive elimination that is going on in here. Okay, I hope I'm briefly able to tell you today that two important industrial processes: hydroformylation as well as Monsanto acetic acid process. By utilizing the simple principle that we have discussed so far in these classes, we have seen.
If
Yes.
we'll take carbon dioxide in place of carbon monoxide, then what would be the reaction? Whether
In
it will
this,
react in presence of HI?
carbon dioxide actually will not be that activated. So see, carbon dioxide, carbon is already +4 oxidation state, right? 2 oxygen is -2 -2. Carbon dioxide is relatively inert gas. Okay, so carbon monoxide on the other hand very reactive. Okay, so carbon dioxide unfortunately in these cases will not be a great gas. It is not going to be a great gas at all for these purposes. For carbon monoxide, carbon dioxide, you can do little bit different type of reaction. I mean, this sort of reaction can be done. You would be able to get, of course, a protonation if you are having. Okay, still you can get carbon dioxide activation that would give you acid type of molecule as well, but in these cases with these catalyst you will not be able to get. Okay, carbon dioxide activation is possible just like carbon monoxide, but these are little bit more difficult reaction. Okay, maybe I'm not sure whether we will be covering it, but in these cases with these catalytic system it is not really a great gas to incorporate. Okay, that not to say that carbon dioxide cannot be involved. Okay, carbon dioxide can be involved into similar, not exactly same type of reaction, similar type of reaction, but that in this type of reaction, this catalytic condition, carbon dioxide is not a good gas. Okay, and also the carbon dioxide binding is little different, right? It's a linear molecule, and overall binding, making it bent is one of the major important things. So carbon dioxide being linear, that is one of the problem or one of the energy demanding processes to make them bent, because all the product that you get are bent, right? If you look at, let's say, acid carbon dioxide, if you are trying to prepare it from carbon dioxide, then that energy barrier is required is very high. Okay, industrial process has to modify, the catalyst need to be used little bit different. Okay.
Sir, definitely carbon monoxide is a very dangerous gas. Please,
Yeah,
sir, what is the temperature we require for this reaction?
these are even, I mean, no, there are processes now available which can make it moderate, even up to room temperature these can be done. Okay, but all these would be dependent on many different reaction conditions. Many research of course has been done depending on the ligand. See, this rhodium, there is always another ligand there. I am not drawing it here, usually a phosphine based ligand or other different type of ligand you can use depending on the ligand. Usually I would say from room temperature to 100 degrees C, these are good enough for these reactions. Okay, of course if you have a better ligand, then you have lower temperature. If the ligand is not good, then you need to use usually a very high temperature. Okay, as well as the side product may be forming. The problem for these sort of reactions are very simply you can have many different type of product formation in the process. Of course, this acyl iodide you need to hydrolyze, right? You need to hydrolyze to give you the acid COI, and then you add water, you get acetic acid. Hydrolysis basically. Now, in these particular cases, if you do not have enough energy involved or enough temperature given, this transfer, methyl transfer onto the CO may not be happening effectively. Okay, and sometimes this reductive elimination step, this iodide and this acyl CH3CO, this is the acyl unit, this step can also be not very fast. So all these processes will be assisted by the ligand. Ligand is usually the these are also ligand, iodide, acyl, these are also ligand, but these are the reactive part of the ligand component. These are not the one which will stay with rhodium all the time. These ligands could be like, let's say, phosphine type of ligand, let's say triphenyl phosphine type of ligand. There are many different type of ligand is possible. Depending on the rhodium and iridium, ligand will vary, but main important thing is to make it industrially relevant, you need to see the amount, the temperature, what is the temperature involved, what is the cost of the rhodium. So the ligand has to be also that ligand, extra ligand that is required, which is always there with the metal, that has to be cheap, readily available. Sometimes a very fancy or exciting ligand is there which can make this reaction very easy. But what happens that those price of that ligand is very high, let's say. So the price of vinegar or acetic acid we know is not that very high. But in the process, to prepare it in very useful scale, if the price of the ligand is too high, then that's not going to be industrially viable. Of course, as you may know, rhodium and iridium are very expensive metal, right? The good thing is, of course, that these metals are required very, very tiny amount for these reactions, right? So all these cost factor comes into picture while we are looking at the preparation of these commodity material. These are commodity material, like vinegar is a commodity material. Methanol is also a commodity material. Carbon monoxide, although poisonous, but industry uses it like a lot. Okay, so because this is a C1 carbon unit, one carbon insertion. So methanol was having one carbon. Acetic acid is having two carbon. So the second carbon is coming from carbon monoxide. Both of them are cheap source. And the material that we prepare has to be cheap. If it is expensive, many processes will, let's say many pharmaceuticals, many agrochemicals, many fungicide will be very, very expensive if these processes are expensive. So
Sir, suppose more than one gas is available. Suppose carbon monoxide, carbon dioxide, then hydrocarbon, some other hydrocarbons are available. Then whether this methyl alcohol will react with this carbon monoxide and to form acetic acid.
Yeah, this process is relatively facile or easy. Yes, even if you give many other things, the selectivity for this reaction will be high. Okay, let's say carbon monoxide, carbon dioxide, or other alkane or different things are available, as you said. Even though many gases or other things are available, this is the reaction. And particularly also you have a catalyst which is basically best for this sort of reaction. So any other reaction that might be feasible may not be that easy compared to this reaction under these catalytic condition or under these reagents. Okay, so this reaction will go on very smoothly. And in industry, as you know, I mean, if you need these two reagents only you will use. It's not that there is carbon dioxide is also present in large quantity with carbon monoxide. Okay, even if it is present, that should not be too much of a problem. But as you know, when industry does it, they will take a cylinder of carbon monoxide, a good liquid. Methanol is just like ethanol. Methanol is similar looking. The liquid, this is a liquid, this is a gas. Of course, liquid gas mixing is another engineering problem you have to deal with. Overall, you have to have this catalyst ready. These can be usually, I mean, a lot of cases it could be heterogeneous catalysis, need not necessarily always be homogeneous catalysis. But overall, this reaction goes on very smoothly, irrespective of the other things present. So yes, to answer your question.
Sir, this question, yes, sir, you have answered very nicely. Sir, why I asked this question? Because suppose from a stack or some emissions, so many gases are coming out, and if we want to get some good products from that emissions without going for absorption process, then if possible, then we can produce acetic acid over there. Simultaneously, some other gases will be leaving. if some other gas.
Sure. So a lot of those things have been tried and successfully tried, depending on the combination of the gases and the catalyst being used. Definitely, it could be one of the ways to, as you said, take out selectively one gas and remove or utilize other gas mixture for other purposes. Yes, that can be done. But as you know, in industry, everything has to be cost effective. The source of things has to be reliable. There are many other products you can also think of making to acetic acid, right? So the industry decision is, of course, dependent on many things that different industry will take it up in a different way, right?
Actually, many people are working on conversion of carbon dioxide to methanol.
Yes, of course, we are also working towards that. Yes.
Yes, sir. So if we can, if mixture of gases are there, and if we can produce methanol from carbon dioxide, again carbon monoxide present over there, then methanol, carbon monoxide, again it will react, it will form acetic acid. So it will be very good.
Yeah, sure.
With a very good product without leaving the unwanted or dangerous gases to the environment. We can follow that. So that in that
Absolutely.
thing came to my mind. So that I asked, sir.
Absolutely, it's a good idea. Again, as I said, the decision to go for which product or which thing will depend on the many factors, right? Reactor, what type of reactor they do have, what is the reagent they do have, or what they want to produce, the cost of goods as well as the cost of the products. So it's usually, I would say, this is a decision industry make based on the many factors. Of course, what you said is correct. It can be utilized as a selective process for doing a particular thing and then leaving rest of them aside that can be utilized for other purpose. Okay. Thank you all. So today's first class is over. I will have another class, of course. So I'll come back in a moment. I am coming back. Thank you very much. See you soon.
जिनको जल्दी ड्यूटी करना है देखिए आप जानते हैं ये जगह डेवलप कर रहा है 17 नंबर से आप किसान कॉलेज में ना वो जगह मंडी पर मंडी किसान कॉलेज
हाँ ममता Mamta, can you, yeah, that's fine. Both Mamta and Krishna, I will take maybe 5 minutes break and then I'll come back. Is that okay?
Yeah, it's fine. Absolutely
Fine.
fine.
Yeah. Okay. 5-7 minutes break or 5 minutes, let's say.
Yes,
And
yes, you can take some.
we'll come back and meet again here. Another hour we'll have. Okay. Sure.
Yes, yes.
Sure. Yeah, coming back in 2 minutes. Yeah, hi. Coming back in 2 minutes. Okay. Hi, hello everyone. Can we start?
Yes, sir. Yes, sir. We can start.
Okay. I thought I have stopped recording.